All right, everybody, here we go. The derivative as a function. So we have this definition of the derivative, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. The only difference between this formula and one I wrote earlier is simply that this letter here is no longer the letter a, which stood for a constant number, but now it's a variable. It's the letter x. That's really the only difference. Mathematically, it's going to mean something a little bit different, but computationally, it's really the same idea. So here's an example. Suppose a particle is moving along the x-axis, and we can measure its distance from the origin at time t using the following equation. Find the function that will give the velocity v of t at a particular time. So rather than saying, what is the velocity at time t equals 4, now I'm saying, give me a function that I can just plug in the number 4 to. Or I can plug in the number 8 too. So I don't have to go back through and find the limit every single time I want to find an instantaneous velocity. Now I'm going to create a function that tells me the instantaneous velocity at any particular time I wish. That's the goal here. All right. So let's start off with building it up kind of from scratch. Before we do that, I'm sorry, getting ahead of myself. Let's talk about what the function might look like. So here's a graph of f, okay, f of x. And here's the graph of its derivative, f prime of x. And let's just kind of take a look and see if this kind of makes sense. So first of all, this is obviously a cubic function. It goes up, down, up. Okay. And this looks very much like a quadratic function, down, up. And let's see kind of how this works. I'm going to make some vertical lines on here to help us kind of see what's happening. All right. So remember what the tangent, the slope, the derivative of f does. The derivative of f measures the slope of the line tangent to the curve. So we look at the slope of the line tangent to the curve here. If I were to be drawing, and this is going to be difficult, but if I draw kind of a line tangent to the curve over here, that's a pretty steep, very positive slope here. So the measure at this point is going to have to be a very positive number. And we can see that if we kind of go down from there, here's the point I'm talking about. If we go down from there, well, it's pretty yellow, it's hard to see. The value of the function is off the charts big on this graph. Okay. Let's look at another point. Okay, let's look at another point. Let's take a look at the point maybe up here near the peak. Okay, maybe right about here. Let's see. Right at this intersection here, I'll make a little dot so you can see where I'm talking about. Right about here, let's try to figure out what the slope of that line might be that's tangent to the curve there. So I'm going to try again with this. Not too terribly bad, not great, but let's see, maybe I can alter it a little bit here. There we go. Maybe something like that. It's a little too steep now, a little not steep enough. There we go. That's pretty close. Okay, so the slope of that line is going to be the value of the derivative at that point. So I'm going to go ahead and I'm going to make a vertical line so you can see how this relates to the derivative graph. The derivative graph is down below. Okay. So the derivative, the value of the derivative at this x value, this pink x value, the value of the derivative looks like it's about 5. What that means is that when x is equal to this value, which looks maybe it's about 1, okay, then the derivative is about 5. So the slope of this line should be about a slope of positive 5. And that kind of makes sense, right? Okay. It's a steep slope, okay, and we get a large value for the derivative. Okay, let's try some other things. Okay, let's look and see what happens right about here, right at the peak. Okay, now this is kind of an interesting point. So what is the derivative of that point going to be? It looks like the tangent line is just going to sit right on top of it. Okay, it's a constant function. Okay, that's not what I wanted to do. Okay, well, pretend it's sitting on the line. It's a constant function, so the slope is going to be 0. That means that ideally, if I move straight down, if I look at this is the value at x equals, looks about 1 maybe. Yeah, at 1. When x is 1, the slope of the tangent line is 0. That means that the derivative function should cross through the x-axis at that point, and it does. Okay. So that's what's happening here. As we move to the right here, the slope is going negative, 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 negative. Okay, and you'll notice again, negative, negative. The value of the derivative down in this region from here to here is all negative. Again, when we get to this turnaround point here, the slope of this tangent line to the graph here, at this point right here, again, it looks like about +1, is about 0. Okay, it's a horizontal tangent. So ideally, at this point, not because the graph hits 0, but because the tangent line is a horizontal line, the slope is 0, and therefore you see that the derivative function hits 0 at that point. Okay, so that's the relationship between f of x and f prime of x. And this is a really important idea. As f of x increases, f prime of x is positive. When f of x decreases, f prime of x is negative. When f of x increases again, it's positive. So we can actually summarize that. We can say when f of x is greater than 0, when f of x increases, f prime of x is bigger than 0. When f of x decreases, f prime of x is less than 0. And when f of x hits a maximum or minimum, f prime of x is 0. Really important points here. And if there's nothing else you get from this slide here, you should absolutely have this deep in your heart. Okay. We're going to use this picture to try to get a sense of what would happen to the derivative. Okay, so I'm going to go ahead and make myself some axes over here, and I'm freehanding this with the mouse pad, so bear with me. But I think we can do it. Okay, that obviously wasn't freehanded. Okay, so we're starting at 0, so actually I can start these, make it like this. And initially we start by decreasing down to 2. 2 is a minimum. So we decrease down to 2. That means that f prime, which this graph is going to have to be negative. So here is 2. Once we get to 2, we hit a minimum. Minimum values on f prime are 0. Okay? So we know that the derivative function is negative until it hits 2, at which point it's 0. Okay? Then the original function increases from 2 to about 3.5. That means that the f prime has to be 0 here as well. That's 3.5. 3.5. Oh, again, I'm freehanding, so bear with me here. So between here and here, it must be positive, because between 2 and 3.5, f of x was increasing. From 3.5 to about 7, the original function was decreasing, which means that from 3.5 to 7, the derivative function over here must be negative. When it hits about maybe a little less than 7, we hit a minimum again. And remember, minimums are zeros. So there's a 0 right there. So it's going to be negative in here. Okay? And then beyond 7, it's increasing, so the derivative is positive. So there's your f prime graph. Not the prettiest f prime graph, but f prime nonetheless. Okay? Very nice. Okay, differentiability comes from the idea of continuity in some ways. So differentiability just says the function you can take a derivative at. Okay? A function is differentiable if the derivative exists at that point. So remember that the derivative is the slope of the tangent line. Okay? So the slope of the tangent line has to be changing. So let's take a look at the slope of the tangent line of this thing. Okay, and we have to be able to hit the tangent line in both places. All in here, it makes sense to talk about a tangent line, tangent line, tangent line. This point, though, is a little weird. It's continuous, but try to figure out what the tangent line would look like. What does it look like? Is that the tangent line? I mean, it could be just about anything. So this function, doesn't really make sense to think about a tangent line at this point, because if we approach it from the left, the tangent line looks like it's going to be kind of like that. And if we approach it from the right, it looks like the tangent line is going to kind of be like that. It's impossible to know what the tangent line should be at that point. This function is not differentiable at this point, at the point x equals 5.6 roughly. How about this one? Now, here's the point, and again, at x equals 5, as we approach from the left, we get a tangent line like that, but if we approach from the right, the slope of the tangent line is like that. Impossible to know which one we should be using, because remember, the derivative is defined as a limit. Okay, so you have to be able to approach it from both sides. This function is not differentiable at this point. It's also discontinuous. So that's another thing we can think about. If it's not continuous, you can't take a limit, and so therefore you can't have a derivative because derivatives are limits. This one has a limit but does not have a derivative because the limit of the derivative of the difference quotient doesn't exist. This one, really nice and smooth. So when you think about this, continuity, the formal definition was the limit as x goes to a of f of x equals f of a. Same thing with differentiability has a formal definition. The limit exists, the derivative exists because the limit from both sides exists. But when we think about differentiability, we can think about it being a smooth continuous curve. Right? None of these cusps, none of this business, right? Nice and smooth, right? So continuous can have jagged edges. Continuous functions can, but differentiable functions cannot have those jagged edges. It has to be smooth. Okay, so let's just take a look here and see where is this function non-differentiable? Well, okay, we're going to have, looks like pretty nice in here. We get to this cusp right here. Again, it's hard to figure out, is the slope going to be this slope or is it going to be a slope that's kind of moving in this direction? We're at a jagged edge, we're at a cusp. This point is non-differentiable. Okay, so maybe I'll highlight that point. Problem point. Okay, this is all good in here, but once you get to 4, remember the limit has to exist from both sides because the derivative is a limit. Not going to work. Okay, it's not even continuous, so it can't be differentiable. And at 5, again, we have a jagged edge. So anytime you have a point, some kind of jaggedness or discontinuity, we can't be differentiable. So the best words that I use here are going to be smooth and continuous. Smooth, just like Mr. Null doing calculus. All right, with that, we're going to take a break here and go on to derivative shortcuts.